Hello everybody, Adam Lusek here, and today we're going to talk about vector databases. With the rise of language models, one of the things that's been really popular recently are retrieval augmented generation pipelines. And RAG pipelines basically consist of being able to dynamically insert different documents as context within a language model's prompts to both ground and add maybe some specific knowledge to the language model's generation. But actually retrieving that context or documents to insert into the prompt dynamically relies on one very specific thing: a vector database that can take a user's query and find similar documents that might be used to answer it. And this is a new way of really looking at databases, as we need to be able to somehow capture the meaning of a piece of content and then be able to store it in such a way that we can find not the exact documents, but similar ones. So in this video, we're going to start from the bottom and show how the meaning of a piece of content is actually captured in such a way that it can be represented numerically, and then how all of those representations, which are called embeddings, are actually stored within a vector database and then also retrieved from a vector database. And then finally, once we've built up all of that understanding, we'll put it together into a retrieval augmented generation pipeline to show from the ground up how all of this works. And so the first step really is understanding how a piece of content can be converted into some form that can be mathematically manipulated, yet still capture the semantic and contextual meaning of that piece of content. Essentially, some string of numbers that captures the meaning of some words. And so to display a little bit of what I'm actually talking about, I'm going to be using OpenAI's embedding model, Text Embedding 3 Small, to generate an embedding for the word hello. And so if we run this, what we'll see is that it's returned essentially what appears to be a list with all sorts of values in that list. The number of values in this list that makes up the embedding for the word hello are called dimensions. So in total, this is returned 1,536 dimensions embedding the meaning of the word hello. So essentially, we've converted the word hello with an exclamation point to numbers. And these numbers are supposed to capture the meaning of the word hello. And now that it's in a numerical form, allows us to run all sorts of different mathematical operations on it that can be later ingested by other neural networks, or more importantly, inserted into a vector database. And so you're probably wondering, what do you mean by these numbers actually representing the word hello? How can these numbers actually mean hello? And what do you mean by the dimensions? Like, we live in a three-dimensional world. And how can hello be represented in 1,536 dimensions? Well, let's get into all of that now. And so to understand that, it really all starts with the idea of a vector. And a vector in this case is some sort of mathematical structure that has a magnitude, or you can think about it as size, and a direction. For our example here, we can think of the vector as some point in space, with the direction being an arrow from the center, 0, 0, to that point in vector space. Right here will be a representation of the vector 1, 1 in 2 dimensions. Adding on a third dimension, we can see with this example of the vector 2, 3, 5 that it's now a point in 3D vector space with the direction of this arrow pointing towards it, and then its magnitude or size relatively being the length of this arrow. And as a bit of an aside, you're likely more familiar with the idea of a vector if you've taken some sort of, high school or early level physics class. Because in physics, they use vectors to calculate natural things like velocity, momentum, force, electromagnetic fields, and weights. And I remember one of the things that gave me a hard time in my high school physics class was trying to figure out kind of where the forces of friction are. So inserted this example, but you can see that that's how they actually calculate things in physics. But why are we using vectors here now in the context of machine learning? Well, they provide a very compact way to represent multi-dimensional data where each dimension of the vector can actually correspond to a different feature or attribute of the data, essentially capturing all of what you might understand about some idea, some concept, or some piece of content within that vector itself. And then also, it helps that vector operations like addition, subtraction, dot products are very, very optimized for efficient computations on things like CPUs and GPUs. And then one of the things to understand actually is that the different neurons within an artificial neural network actually process and output vectors themselves. So we can understand that actually representing data as vectors is very useful when doing things like machine learning and doing things that involve different artificial intelligence-based operations. But that doesn't answer our question of how are we actually able to encode the meaning of an idea, a concept, or some piece of content like a blog post per se or a PDF document into a vector. And so I've put together a bit of an abridged timeline of how people have actually started to think of putting together vectors that can represent ideas. And the simplest idea of an embedding is what's called one hot encoding. Essentially, for every single word that you're interested in, one index of this vector is going to be turned to 1, and that will represent that idea. The rest of the entries corresponding to the length of your vocabulary per se, which in this example here would just be 4, is going to be turned to 0. So what that's able to do is actually capture the idea of, let's say, Rome here in the first index of the vector, so that when we actually look at a vector that has a 1 in the first place and then the rest being zeros, we would know that that represents Rome. And then the subsequent words in our vocabulary size can fill up the remaining indices. And so now if we look at a vector of the same length, but let's say there's a 1 in the second spot and then zeros all else, we'd know that that would actually represent Paris. So we're not looking at Rome right now, we're looking at Paris if that 1 is in the second spot. And so while this is very straightforward and useful, and we can see how we can capture the meaning of a word within these numerical representations, it comes with a few different issues. One of them is sparsity. If we have a large vocabulary or a lot of words together that we want to represent this way, most of our vectors are actually going to be filled with zeros. And this is relatively inefficient for what we want to do. Additionally, it doesn't capture any specific semantic information or meaning or relationships between words, either contextually or where they're placed, things like that. We can store the word, but not necessarily its meaning. And then also, it's not going to be able to handle encoding words that are outside of the vocabulary range or the amount of words that we actually want to represent like this. And so to address these limitations, researchers started looking at more frequency and contextual-based solutions. And so this brings us to kind of the next step here, the co-occurrence matrix. And so this operates under the assumption that the frequency of words appearing in similar contexts likely have more related meanings. So for our example here of I like deep learning, I like NLP, I enjoy flying, we can see that for the co-occurrence matrix vector here now of the word I is going to be 0 and then 2 once it's by like, because right now it's next to like, twice here with I like deep learning, I like NLP, and then once by I enjoy here, so I enjoy, and then zeros all else. This is starting to give us a little bit more of that contextual understanding. We might even be able to glean something like, oh, I is generally put towards something that represents, the enjoyment or the liking, something like that, as it occurs frequently near words of that meaning. And looking at individual words representations like this brought about some advancements that one hot encoding lacked. Things like capturing some of the semantic information, so words used in similar contexts will tend to have similar vector representations. It provides a much richer representation since each word is represented by a vector of co-occurrence counts rather than a single one in a very sparse vector. And then this can also handle out of vocabulary words because new words can now be represented based on their co-occurrence with known words. But we still maintain some limitations with this. There is, of course, this high dimensionality. The size of the matrix actually grows quadratically with the vocabulary size. It also suffers from some of the different sparsity ideas that we were talking about that one hot encoding really suffers from, as many words may never co-occur, leading to all sorts of zeros being inserted in there. And then, of course, this really lacks the fine-grained semantic relationships between words. It captures some of the context and is getting much better at it, but it doesn't really fully represent these complex language patterns and understandings. Which brings us to modern-day embedding models, which are similar to what we just saw when we were embedding the word hello, exclamation point, using OpenAI's embedding. And these take advantage of already pre-trained things like language models, things like generative pre-trained transformers, to actually create very rich, context-aware representations of words and concepts, addressing much of the different limitations of the earliest methods and offering very powerful capabilities for downstream tasks. And the great part of actually leveraging these more advanced models specifically designed to do that is that they can generate different representations for the same word based on the context in a sentence. This finally allows us to capture very rich contextual understanding, such as distinguishing between different meanings of the same word based on the context of where it's used, maybe in some piece of content or the sentence that it's in. And this takes advantage of these large-scale deep learning models, many of them being language models that are trained for things like next word prediction or masked language models to insert into a sentence the word that it most expects to be there. And through training all of these on a massive amount of text and data, they actually learn to represent almost anything as these high-dimensional vectors. And one of the interesting ways to think about this is actually the embedding that's created is this language model's internal representation of that idea. So you can almost take something like a task-specific language model, one that might predict, just the next word, and remove that last task-specific layer, and then suddenly that model has become an embedding model, just outputting its internal representation of the task before it's finally transformed into some sort of prediction. So we've seen people actually take things like, Llama 3 or Mistral 7B and actually shear off the final layer that creates and predicts the next token and use that output as actually the embedding. So running your query all the way through all of the layers of the neural network, and then that final, right before the last step where it does the predictions, representation of your query is then going to become the understood embedding. And through the deep learning and training process, this model is expected to very richly represent these ideas in this numerical vector fashion. And then, of course, models are also trained specifically for embedding and representing things as vectors. We've, of course, seen the OpenAI example right at the beginning, but they can also be specifically trained for different tasks. I've seen things like multilingual embeddings or the idea of Instructor XL, which can actually take in instructions alongside what you want to embed to create task-specific embeddings, and then also different modalities, actually embedding things like images and videos or audio files into these vector representations as well. Great. So now that we understand a little bit about how these embeddings and vector representations of data and content are actually generated, we now need to look at what can we actually do with that. And so what I've said here is that embeddings are very useful when they're flowing through something like a language model for different calculations and predictions, but we can also take advantage of these meaningful dense vector representation of content and ideas, more specifically by being able to actually compare vectors together very strictly and mathematically, giving us a measure of the semantic similarity between words, sentences, or even entire documents. And this comparison is what will allow us later on down the line to actually be able to find similar documents to what we might be querying for to return the context that we need for a retrieval augmented generation pipeline. So very crucial to be able to actually strictly and mathematically compare the ideas and concepts together to see how similar they are. And so to do this, let's actually look at a few different visualizations of this first. To start, what I've put together is a list of 100 different words across 4 different categories: animals, food, weather, occupations, and generated already their embeddings using OpenAI's embeddings. So now we have all of the words, what category they're in, and then also their dense vector representation created by OpenAI's embedding model. And so let's actually visualize these to see how these different embeddings interact with each other in that aforementioned vector space that they rely on. And of course, we must note that the embeddings that we generated are actually 1,536 dimensions, where each dimension might capture some sort of feature or different understanding about what that word is. And of course, if we're thinking about this in terms of, graphs and visualizing it, we as humans really only understand 3 dimensions. So visualizing these embeddings can be a little bit tricky, but let's show 3 different representations from 1-dimensional up to 3-dimensional to get a better understanding of this. Starting with visualizing a vector embedding for a couple words in 1 dimension. And this graph here does exactly that. It goes up across all of the different dimensions, and then I have a color scale for the different values. And so a value that is more negative is going to be trending towards blue, whereas a value more positive is going to be trending towards red. So across this, we can see a little bit of a 1-dimensional visualization for the embedding of dog. We can see that maybe, this dimension here might capture a lot more of the meaning of the dog as it's a much higher value. Or around here, it's a little bit hard to say with these machine learning things what the actual values actually mean, since it is something that's learned through this training process. But we can see that the embedding for dog is not the same as the embedding for mango. There's a lot more higher values here. There's a lot more lower values here in comparison. There's a couple different similarities, but this one right here, this dimension is really red, whereas that doesn't necessarily exist in the embedding for dog. And so going through here, we can see across a couple different categories for dog, for mango, a visualization for pilot, and then a visualization for breezy, which has some very low values right here, that all of these are going to be a little bit different, but capture some sort of meaning within this. But obviously, it's not super easy to actually compare how similar these embeddings are in a 1-dimensional space. So let's move up to the 2-dimensional representation. And so of course, it's very hard to go through 1,536 dimensions and then convert that down into a 2D representation, but we'll be taking advantage of the t-distributed stochastic neighbor embedding model that's actually able to reduce the dimensionality of these embeddings down to 2D that will allow us to then plot and observe different patterns, clusters, or relationships within our embedding space, and it preserves a lot of these relationships that are captured within those high dimensions. So let's actually run this and see how all of the embeddings turn out on a 2D representation. And so this is where we're starting to actually see a lot better the relationships between the embeddings and the words and where they're placed in this vector space. We can see some very clear clusters of occupations up here in the top left, more of the animals here in the middle left, the different weather words are down here in the bottom right, and then in the middle right, a lot of our food ends up here. It's also interesting to see here that the food and also a couple of the animals here are starting to blend together a little bit here in the middle. So this would make sense as some of the things here like, rabbit, frog, deer, and I guess according to these embeddings, bear, would be similar to something like fish, which is both an animal and a food or other different foods. So it starts to get a little bit blurry, but we can see that they're grouped a little bit together because their meanings are understood contextually and semantically to be similar. So this is a great representation to see how some of these actual understandings and vector representations are placed into the vector space, but I really enjoy looking at 1 dimension higher, the 3D representation. Great, so now this is going to give a much better understanding of actually understanding in a higher dimensional space how the actual machine learned understanding and representation of these words actually places these things. We can see that there's 4 very distinct, almost clouds here of words that we saw clustered in our 2-dimensional representation above here, but this shows a little bit more of the nuances of that high dimensional space. So we can see, of course, in green, the food, in red, the animals, in blue, the different occupations, and then in purple, the weather. And some of the cool things to think about here is that we can actually see that very similar things are placed closer together. So stuff like firefighter right here and policeman are pretty close, whereas like policeman and plumber are a little bit further away. If we look at the different weathers here, we can see that sleet and hail are close together, whereas things like dry and hot and warm are more around here. And then, of course, going back to our different blur of animals versus foods, we can see that they're in general placed closely together, and then some of them, like fish, here we go, like fish here is actually a little bit more in line with the actual animals over here, but they're all placed in generally the same area. So this is a great representation to start seeing some of these relationships with how these different dimensions actually capture the understanding. But of course, this is where the visualizations unfortunately stop for us, as we don't necessarily understand things in a higher dimension than 3D. But you can imagine that the more dimensions, the more specific an idea can actually be captured in. And so that's the idea of the high dimension embedding vector of something like a word, a piece of content, or an idea. So as we've been seeing, similar things are actually placed in similar places in high dimensional vector space. And this is phenomenal for us because now what we can do is actually compare these 2 points to calculate sort of how similar something might be. Calculating this similarity is going to be crucial down the line as we work towards putting together this semantic-based retrieval of context for our different RAG pipelines. And also, the concept of closeness between vectors is super central to understanding these semantic relationships. In the context of word embeddings, 2 vectors may be considered close if they actually represent words used in similar contexts or related to similar ideas. And so the great part is that now that we have these concepts and content represented numerically, we can actually run some relatively simple mathematical operations to calculate the different distances between them. Starting with the simplest idea of the Euclidean or L2 distance, this is essentially just going to measure the straight line distance between both of those vectors. So if we have vector A here, which ends at this point on this arrow, and vector B here, which ends on this point in this arrow, we can calculate the literal distance between them, which in this representation will be in 2 dimensions. And that's how we can find out how, close they are together. So in the end, we would understand that comparing 2 vectors in their Euclidean distance, if it has a smaller distance, then they are more similar, and a larger difference, then they are more different. We can use a little bit of geometry here and how triangles are kind of calculated and whatnot to figure this out, but it's essentially just going to be the sum of the squared difference between each dimension in the vector and then the square root of that total. So I put together this as a math string here and a function, and we can actually compare now the Euclidean distance between a couple words. So I'm going to do hot and cold, and then hot and programmer. Looking at the output here, we can see that the Euclidean distance between hot and cold is 0.944, and the distance between hot and programmer is 1.29. So we would assume that hot and cold are more similar than hot and programmer. And this would make sense, which if we look here and try and find where hot is, so here's hot. Hot is very close to cold here, whereas hot right here, and then programmer, which is, somewhere in this blue up here, is going to be a little more far away. But one of the downsides of this is that it's actually very affected by the magnitude of the different vectors. And what researchers have found is that the magnitude of a vector doesn't actually necessarily play too much of a part in calculating how similar something is, because the magnitude can be sensitive to things like frequency. If something has a larger amount of words, it might have more frequency than something with smaller amount of words, while still being, of a similar concept or idea. And so what they started looking at more is actually the angles of these vectors and where they're pointing at to look at a more fine-tuned similarity measurement. Which brings us to the dot product. product. And the dot product here is not actually a measurement of distance, but rather of direction. And looking at the direction instead of the actual literal distance is useful because as the dimensions of these embeddings actually increase, the calculation of their distance in between each other becomes a little bit less and less reliable. This is something that researchers have found and have called the curse of dimensionality, which is kind of a dramatic name, I would say, for a math concept. However, the dot product is more interested in looking at the distribution of features or the direction of these vectors. And this relies on the idea that documents or items with similar proportions of features are similar regardless of their actual magnitudes. So comparing the angles between different vectors rather than the literal distance between where they sit in the high dimensional space becomes more meaningful in actually representing their similarity in this context. So putting this through our same test of hot and cold and hot and programmer, we can see that we get a larger positive value for hot and cold than we do for hot and programmer. And so what that means is that a positive value really represents that the vectors point in the same direction. And so a higher positive value represents that it points more similarly together. Whereas the other ones, like 0 represents orthogonal vectors, and a negative value might represent vectors that point in opposite directions. So in this comparison with the higher positive value, we can see that hot and cold are more pointing towards the same point in vector space than hot and programmer, meaning that hot and cold is much more similar than hot and programmer. Dot product runs hand in hand with our third and final similarity measure, cosine similarity, which literally measures the cosine of the angle between two vectors in a vector space. This holds true all of the same things that we've been talking about, where the actual direction of these vectors and where they're pointing can tell us a little bit more about the similarity between them than the literal distance in high dimensional vector embedding space. It's going to be calculated with the dot product on top divided by the multiplication of the magnitudes of the vectors here, which is going to be just the simple dot product that we went over earlier over the multiplication of each individual component squared and the sum of it square root times the other vector's components squared, summed, and then square rooted. And the interesting thing to think about here is that actually, if we have normalized vectors, cosine similarity just becomes the dot product. And normalization in this case means scaling the vectors to have a magnitude of 1. So if we're taking the dot product over the multiplication of the magnitudes, this bottom half just becomes the dot product over 1, which is of course the dot product, allowing us for very quick calculations when calculating cosine similarity over normalized embeddings. And so when we actually look at the cosine similarity between hot and cold and hot and programmer here, we see that we get the exact same numbers as we did with the dot product because OpenAI's embeddings are also normalized in this way. And of course, the normalization and flattening of the magnitudes in this case doesn't necessarily matter to us as much because we're not calculating the exact distance between things and caring about that, because we found that the calculation of the angle between vectors actually tells us more how similar something is with reliability. And so most of the time, you're going to see generally one of these three main distance metrics being used in the actual comparison of embeddings. Just running one final example of comparing all of them at once between hot and cold and hot and warm, we would expect that hot and cold would be less similar than hot and warm, which are more similar, and we understand them to be more similar. So we see with the Euclidean distance that hot and cold is about 0.94, whereas hot and warm is closer because the distance is less, and it's 0.8. So yes, with Euclidean distance, this is saying that hot and warm are more similar than hot and cold. And then of course, cosine similarity and dot product, which since we're using normalized vector embeddings are going to be the same here, are showing a less large positive number than we're seeing with hot and warm when we are comparing hot and cold, which means that, of course, the angle is telling us that these vectors are more similarly directioned together for hot and warm, meaning that, of course, hot and warm are more similar according to cosine and dot product. And so now that we can actually compare two embeddings together to show how similar it is, it brings us now closer towards this powerful application of semantic search and semantic-based retrieval, where instead of sort of the traditional key query-based database retrieval, we can use these similarity calculation methods to retrieve similar entries in this database. Adding on 4 more examples to our 100 examples here of parakeet for an example of an animal, cabbage for food, therapist for occupation, and drought for weather, what we can now do is take these newly added on words and their respective embeddings here, and then compare them back to our existing words to see which ones might be the most similar to them. We can already just directly compare these together. So I've gone ahead and compared parakeet and cat, therapist and mechanic, cabbage and orange, and drought and thunderstorm to see sort of the distances between these. But what we might want to do is actually, if we're looking at parakeet, calculate the distance between all of the entries, the other 100 that we have now in our data frame here, and find which ones are the closest. So that's what I'll be doing here with cosine similarity, running cabbage, drought, parakeet, and therapist through this, and then returning back the top 5 similar now words. And so what we see now from the output is that when doing the calculations with cabbage, we see that the food most similar that lies within our very rough representation of a vector database would be cucumber, followed by lettuce, followed by carrot, broccoli, and potato. Of course, some of these are going to fall off as we reach that 5th word, as it's a very limited data set of only about 25 entries per category here. But moving on to drought, we can see that drought is most similar to dry. Parakeet is actually most similar to penguin, funnily enough, by a long shot here. And then therapist is most similar to doctor and nurse. So what we've done here is very rudimentary semantic search and retrieval, where we've introduced a new word here to our database of words, embedded it using the same embedding models, and then calculated the similarities to find and retrieve the most similar entries within our rudimentary vector database here, and returning those back to us. So by now you should have a pretty decent understanding of actually how this similarity-based retrieval that happens within vector databases actually works. And for our second part of the retrieval and indexing here, I'm going to go a little bit more deeper into actually how vectors and the vector embeddings are placed into the vector databases and the different searching algorithms that are alongside them. This is going to get a little bit more technical and theoretical about how the inner workings of vector databases work. So if you're interested in that, continue watching. But if you understand kind of the general concept of how it works from the previous examples, feel free to use the chapters, which I'll have set up, to skip to the next part, which will be about actually setting up our full RAG pipeline flow using this. So for those of you who are brave enough to be continuing on with actually talking about the indexing and searching across vector databases, let's dig into the idea of the approximate nearest neighbor algorithm, or efficient techniques for finding similar items in large data sets, which is what vector databases really rely on to trade kind of, perfect accuracy that a traditional database would offer for improved speed, making them ideal for different high-dimensional data and large-scale applications. And obviously, our basic example where we ran the similarity calculations across every single entry in our data frame here up above when looking for something similar to like cabbage is very inefficient, especially as we start to insert more and more things into our vector database. For some more scaled up applications, I've seen as much as 20, 30,000 different entries into single vector database instances for very streamlined applications. And naturally, you wouldn't want to run a set of 30,000 different calculations every single time you're querying the database. So let's see what some of these smart folks have come up with to actually index and search across, with the idea of not necessarily finding the exact entry, but the similar entries. And so the first and most basic idea is the k-dimensional tree, which takes the idea of a binary tree search and applies some fancy partitioning to actually index and search over multidimensional space. And the way that this tree is set up is that it takes all of the points, which in this example is going to be A through G, and it starts at one dimension. In this two-dimensional example, that might be the x dimension. And then it finds the median at the x dimension among all of these points, and then that median divides into left and right two spaces. So we can see this outlined by this line here that is pointing towards 1. And so this divides this entire plane of our points into two spaces, the left and the right. These become the left and the right child nodes. And what happens then is that all of the points that are lower than that median or on the left side become part of that space, and then all of the points that are higher than the median on the right side become part of that space. The dimension is then cycled through. So in our two-dimensional example, that will be the y dimension, and then in each space, the median of that y dimension among all of the points in that space is found and then partitioned again. So we can see the two horizontal lines here represented by 2 and 3 cutting between these spaces that were first made by the first partition into 2 across the median between these points in the y dimension. And this is repeated further and further until either there remains only one point in the subspace, in that case that becomes a leaf node, or you hit some maximum depth that you can predefine. In our two-dimensional space, these become planes, but of course in high-dimensional space, these become what are known as hyperplanes, which split up the high-dimensional space in some sort of way that we can't really imagine in our 3D world. The way that actually searching over this then works is that you start, of course, at the root node, and then you follow the same splitting process along that median calculation of each dimension, which should very easily find out whether or not you need to go to the right or to the left, or in this case to the up or the down, or in high dimensional space, wherever to wherever along the tree, until you end up at this leaf node. So if, for example, we ended up at G, that would be then our best candidate. And then we can calculate the distance between our search query embedding and G, and then the search query embedding to the other plane, which in the case of 6 would be this part on the left side that doesn't contain G. And if it's a less distance to this other side of 6 than it is to G, we might backtrack and actually consider the point F, which lies in the other part of 6, as a next best candidate. And repeating this a few times, we can find sort of our most similar entry to our search query. And so the KD tree is really our most basic approach to this. And similar to things like Euclidean distance, it suffers from high dimensionality and actually being able to partition out these spaces. So that will bring us then to our next way of actually setting up and searching over points: locality sensitive hashing. And the broad idea of LSH here is that we're actually going to be using hash functions in a way that is not very typical to how they're traditionally used. We will be using functions that are actually based on similarity and distance to try and find collisions. And the collisions in this case from the hash function are going to then show us how sort of similar something might be, because if two objects actually collide when going through the hash, it will determine that it is quite similar because the hash functions are based on similarity and distance. So to set this up, you choose a family of locality sensitive hash functions, which might be things like Euclidean distance and cosine similarity, and then you run all of your vectors and embeddings through those hash functions. And then you create multiple hash tables using different combinations of those hashing functions. And then we store the vector in the corresponding buckets for each hash table. So essentially, in the end here, we use different combinations of hashing functions, and then vectors that hash to the same value across all of these different combinations are going to end up in the same buckets. And so for the actual searching over this, our query vector undergoes all of the same different hashing functions across all of the different hashing tables, where it would determine which buckets it would land in. All of those buckets are collected along with all of the embeddings within those buckets. It undergoes deduplication if there's any duplicated embeddings, and then returns our k nearest embeddings once finally running the similarity or distance calculations across that subset. Our third method here is then product quantization, where what happens when setting this up is that all of our vectors are split into subvectors. So this might be, if it's a list of 1,536, might split it up into groups of 5. So now we have a bunch of different subvectors all within 5 dimensions of our 1,356 dimensions. So then all of these subvectors are part of their own subvector space. And within that subvector space, we run a k-means algorithm to produce k number of centroids within that. And what these centroids do is they try to approximate sort of the center of all of those vectors in that subspace. And so we create a bunch of these centroids, and those are then going to be the approximation and compression of the vector representations within that subspace. We're able to actually encode the full vectors using these approximations that are generated by the centroids by actually taking the subvectors, determining which centroid it is the closest to, and then that index actually becomes the representation of that subvector. So we're able to compress down these vectors into a representation that's encoded through these centroids. This one's a little bit more complicated to imagine in your head, so I've asked our lovely friend Claude to create me sort of this overview of it. So what we're talking about now with vector decomposition is taking this original vector and splitting it up, in this case, into 4 subvectors. So this 5.1 and 3.8 becomes its own subvector in 2D space, 1.9, 4.7, its own vector right here, and so on and so forth. And then these codebooks are generated with k-means clustering, which what they'll do is attempt to approximate the centers between these 2D vectors as best as possible with a little bit of random initiation so that they're not all of the same. So as we can see, between 5.1 and 3.8, it becomes 5.0, 4.0, 5.2, 3.7, 4.9, 4.1, all sort of different approximations of what 5.1 and 3.8 could be. And this is done for each subvector space. Of course, with multiple vectors, these will be a little bit different. But then the actual encoding process is then finding the nearest centroid for each subvector. So with 5.1 and 3.8, in codebook 1, we see that the nearest centroid is actually 5.1, is actually going to be this 5.2 and 3.7 entry, which becomes 1. So we know that this is going to be codebook 1 because it's in the first index, and it is the first entry, which starting from 0 is going to be this one right here. Repeating the same process encodes our vector from all the way up here down into this 1, 3, 3, 2. Then actually searching over this space goes a little bit like so. Our query vector undergoes the same splitting into these subvectors, and then instead of actually finding the centers of these, what we do is we compute the distance between the query subvectors in that subspace to all of the centroids that land in that subspace. So we can see that for the first table, which contains 4 of these centroids, all of the distance calculations would be 0.1, 0.2, 0.2, and 0.3 for the subvector 5.0, 3.9 across these. This creates a table of distances within these different subspaces. And then what we can do is we can take the approximations that we have that of our encoded vectors and approximate the distance by actually looking at the table and the corresponding distance calculated from our query subvectors. So for our encoded vector here, what we would be looking at is 1 in table 1, which would be 0.2, 3 in table 2, which would be 0, so on and so forth, which would give us a approximated distance of 0.4. Running this very simple then table lookup and addition across all of our encoded vectors, within that, we can return the vectors with the smallest approximated distances. This one's a bit of a tough one to really wrap your head around at first because it's essentially a way of actually compressing and encoding these vectors and then running the approximate distance calculations over those encodings, but it does significantly reduce memory usage and increase some of the speed for searching in this. And the 5th out of 6 setups that we're going to be looking at today is actually commonly used in tandem with our PQ method. And this is the inverted file index. And the main idea of this is that in our embedding vector space across all of our vectors that we want in our database here, we take different samples. And within those samples, we do the same k-means clustering to find sort of this set of centroids that approximate our centers of the subsamples in our vector space. These centroids are then linked back to all of our original vectors and become the index there. This is where the inversion comes from, because instead of mapping vectors to centroids, we actually map the centroids to their original vectors, creating almost a lossy representation of that sample and area in the vector space. So when we actually search over this, what we're able to do is take the query vector and then find the nearest centroid. That centroid then gives us the list of possible candidates that we should run our more fine similarity calculations over. So where product quantization actually happens within this is that what you can do is with the different clusters that IVF is creating here, you can calculate what are called residual vectors, which is the original vector minus the centroid. And what these residual vectors do is they're more distributed around kind of 0 within this subcluster space here. And then we can apply our regular PQ methods on top of that within each cluster. This effectively allows IVF to narrow down our search space very fast, and then we take advantage of PQ for the fast approximate similarity computations. And last but not least, we have the Hierarchical Navigable Small World, or HNSW, which is right now what I've been seeing kind of the most popular setup for setting up vector databases. So to set this up, we start by determining how many layers we want, which can be some sort of arbitrary number. In this picture example, it is 3. And then the amount of nodes that we have per layer is exponentially distributed. So we'll have all of the nodes at least on the densest layer, which is going to be our bottom layer, and then that is going to be exponentially decreased in the number of nodes that we have going up and up. What I mean by that is that, for example, if we have a 4-layer HNSW and 1,000 embeddings, we'll have at least 1,000 nodes on layer 0, then 250 on layer 1, 62 on layer 3, and then 15 on layer 4. So that is that exponential distribution of nodes. The indexing process then goes as such. Each embedding then is assigned to a node, and the node has some sort of maximum layer that is assigned by this exponential distribution. Starting at that top layer, the node is placed in, and then it is compared with the nodes around it to find the nearest points to it using these distance and similarity calculations. This takes a bit of a greedy search approach, so it'll look through all of them and then insert and replace out until we find sort of n number of connections that we want to make to that node on that layer. And then from that, we make bidirectional connections. So that node is connected to it, and the node that it's connected to it is also pointing back and connected to our node that we're popping on that layer. And so once those connections are made, we use the starting point on this layer that we end up on as the starting point for the layer beneath it. This search repeats until it hits the bottom layer, at which we sort of expect its placement and the area around the node and its connections to kind of represent its general placement in our total embedding space, as we are calculating a lot of the distances between the vectors represented by the nodes along the way. Searching through this then starts with our query vector on the entry point of our top layer, where we do the same sort of greedy search to find the nearest neighbor. And then this goes down and down and down, repeating sort of a similar process to our indexing process until we land on the actual final layer itself. And so once we actually hit the bottom layer, we perform more of a beam search to widen our area, compare the distances of our query vector with the nearest neighbors of where we ended up on the final layer, and that tends to return our k nearest neighbors. This method tends to be incredibly accurate in practice, and so is actually what we'll be using as we transition finally out of the different algorithms and theory here into actually setting up our vector database and showing the full end-to-end RAG. Phenomenal. So welcome back everybody who may have skipped over the algorithms and indexing section. And so what we're going to do right now is apply back all of our understanding that we've gained to create a retrieval augmented generation setup. So essentially what we'll be doing is taking some sort of document, chunking it into different sub pieces of text, and then we'll be using an embedding model to convert those pieces of text into their vector representations and embeddings that are numerically capturing the ideas and concepts within them. We're going to then store all of those into our vector database that we're going to set up, and then we're going to apply all of that back into our RAG flow, which will take a user query, some sort of questionnaire input, return back the best context from our vector database, where it'll calculate the most similar pieces in there to our query and return them, and then use those as context with our language model to produce a response. And so of course, to start, we're going to need some form of content that we want to embed. And so I had this paper downloaded and ready to go. It is the ties merging paper, which I go over ties merging in my recent video, which will pop up on the screen now, about actually merging together different fine-tuned language models for downstream tasks and efficient learning. And what we're going to do is take this paper and chunk it up into different pieces of subtext. And the chunking part is important in the RAG setup because we might have many hundreds, if not thousands, of different documents. And also we can't just put in the entirety of the document into our prompt every single time someone asks a question. What we want to do is dynamically just pick and choose the right parts of our document to actually insert as the context. This is where our similarity and semantic search is going to come into play, as we're going to be embedding all of these chunks of the document and then finding the most similar ones to the user query to insert dynamically into our prompt. So to chunk it, we're just going to be using some LangChain integrations with the PyPDF loader that will load the document. And then I'm going to use a recursive character text splitter that will actually be doing a token calculation on this. So it's going to chunk all of our document, which right now is just going to be one long string of all of the text, and create chunk sizes of 800 tokens. And then the next one is going to have a 400 token overlap, but be the same size of 800 tokens in total. And these numbers are ones that I actually got from OpenAI's search tool parameter in their assistance. They recommend, or at least they use, an 800 token chunk size with a 400 token overlap. So it's usually my default go-to when setting these things up. Performing this chunking results in 62 total chunks that we'll be indexing into our database. And then just a little example of the first 500 characters of our first chunk looks like, yep, it is exactly just the first little bit here, going into from the title to the abstract a little bit of the paper. And so the database that we're actually going to be using is going to be ChromaDB, which is a wonderful open source and lightweight database that I've done a decent amount of work with and is super easy to set up. We're just going to be using their Python integration to set up a persistent client, create a collection within that client, which is where we're actually going to be storing all of our chunks. And then what I'm actually determining here is that I want it to be using the hierarchical navigable small world setup, which we go over in our algorithms and indexing. And the distance measurement I want to use is cosine similarity. So setting that up and actually inserting in our chunks, we now see that we have 62 entries within our collection. We can immediately test our similarity-based retrieval here, where I'll put in what is the process for electing signs, and then it will find me the top 5 results that are similar within those chunks to my query. Printing those out right here, we can see some of the snippets of them. We can see that the actual distance calculation is 0.63 from this. It retrieved chunk 22, and it says, we bring in a more detailed view, yada, 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 all this, importance of resolving sign interference, stuff like that. So what it'll try to do is, taking my text query, return the most similarly embedded chunks within the database. This, of course, will be done by embedding our query and then running over the searching through all of our entries. And so now that we have the retrieval part set up, we want to set up our language model and the prompt to be able to take in the context and the user question to generate our final response. So I'll also be using LangChain along with GPT-4 Omni with this, and my prompt is going to be very simple. You're a data science AI assistant. Respond to the user question below using the provided contextual documents retrieved from a research paper. And then I have a space for documents, and then I have a space for the user question. And LangChain is really nice to use with this because we can dynamically change our prompt and insert in our different data like these documents and the questions with their chain integrations. So very simply, we're going to set up the full retrieval augmented generation here by first taking in the user query and returning the results from our database. And the results are going to be, of course, searching over the database with our query and returning the top 5 most similar results. We're then also going to insert those results into the documents part of our prompt right here. So it'll pop all of that in as text and then attach also the user question. And then that will create a response from our language model, which we will output. So running that with the same query of how does sign election happen at that step of the process? Well, actually first defining the function and then running it, what we will see now is the RAG output. So now what the language model has seen is all of the retrieved context from our query, and then it is responding to our question. So in the ties merging process, sign election step is crucial for resolving disagreements in signs, aggregated elected sign vector creation, choosing the dominant sign, efficient computation. And then by following these steps, you can ensure that the elected sign for each parameter is the one that has the greatest overall influence. From my understanding of ties, this sounds about right, and it is likely that it was able to actually put all of this in. So this is great, a full retrieval augmented generation pipeline using our vector database, retrieving the right documents based on the similarity calculations of our query, and then generating the final response to our question. And so while retrieval augmented generation is a very, very big and important use case for vector databases and the embedding process, I also wanted to highlight a couple of the other different use cases that can be used when thinking about these embedding-based representations. The first other use case is, of course, clustering, which it already kind of essentially is doing. And so what you can do is use embeddings to group similar things together, and you might even be able to, reveal hidden patterns or themes within your data that you're running through embeddings and then comparing them together too. The second one would be recommendation systems. Actually comparing what, let's say in an e-commerce setting, a customer might be viewing, or even in something like, let's say, listening to music, what someone's listening to, or maybe the videos that they're watching, having some sort of recommendation engine back to the customer or the user based on the similarity between one piece of content or one product and then another one. You could compare the embeddings of different items that a user has interacted with to other items in some database to actually serve different similar content. The fourth here might be anomaly detection, actually being able to identify unusual or anomalous data points that don't fit well with the rest of the data set. This is super, super useful for things like fraud detection or unusual network traffic for cybersecurity. And what you can do is actually look at maybe the signals and compare them together. And if you have some sort of learned embedding system for those different data points, you can see which ones are actually outliers. And those would be the anomalies which might represent something going wrong in the general flow of your system. Following that, we could look at different diversity measurements, actually examining the distributions of embeddings in a data set. You can kind of assess how diverse the content might be. This could be useful for things like content curations to ensure a wide range of perspectives, or maybe even academic research to evaluate kind of the breadth of a literature review. And then finally, we have, of course, classification. Embeddings can be super useful to classify content into different predefined categories by comparing the embedding of a new piece of content to the embedding of a known category. This is useful for things like zero-shot classification, especially in the terms of image-based classification, to actually segment out what images actually fall into which categories. And so with that being said, I hope by now you have a very good, deep understanding of how vector databases and kind of these embedding systems actually work, are able to encode the meaning of something into numbers that can be used for further different mathematical processing to tell us things like similarity or distances for downstream tasks. If you enjoyed the video, consider leaving a like. If you want to see more like this and support the channel, please subscribe. And of course, if you have any questions, leave them in the comments below. Thank you and have a good day.